Okay, a 1 liter volume of air initially at 3.5 atmospheric pressure, atmosphere of pressure, is allowed to expand isothermally until the pressure is 1 atmospheric pressure. It is then compressed at constant pressure to its initial volume and lastly brought back to its original pressure by heating at constant volume. Okay, draw the process on a pressure volume diagram including numbers and label for the axis. Okay, I purposely draw these three graphs just for temporary use. Okay, first of all, let us identify how many processes are mentioned. Okay, so here you say a 1 liter expand isothermally. Look for keywords, yeah? Look for keywords, expand isothermally. This one compress at constant pressure. And the last one is heating at constant volume. Heating at constant volume. So, okay, so the first one is isothermal process. And this is the first one. And the second one is constant pressure is isobaric process. And the third one is constant volume, isochoric. Okay, so this is the first process, and this is the second process, and this is the third process. Okay. Okay, so now how to combine all this graph? You need to draw a pressure volume diagram like this one, including all the numbers and labels. How to combine all this graph? So first of all, you can draw separately, predict how each process looks like. Yeah, I just draw this graph like here. You can see that when the graph going up is pressure increase, the graph going to the right is volume increase. When the graph going away from the both axes, pressure and volume, when going away from both of the axes, the temperature increase. As you can see the isothermal line, each line represent a temperature. Okay, the line which is nearer to the axis, lower temperature. The line which is isothermal line which is further away from the axis is higher temperature. Okay, so look at the first one. First one, he say expand isothermally. Isothermal process is, isothermal process is we can say is like isothermal means constant temperature. Constant temperature, that means must move along this isothermal line. So it's either let's say I start from here. It's either I expand. It's either I going down or going up, isn't it? Going down or going up. But which direction do you think? Which direction he said? Expansion. Here he mentioned expansion. You see that? Expansion. So expansion, that means the graph should be going to the right, not going to the left. Going to the left is compression. So the graph should actually go. So this one is wrong. This one is correct. The graph should go down. Yeah, go down. Go to a bigger volume. Okay. Okay, good. Next, look at the second one. He said compress at constant pressure. Constant pressure, that means it must maintain. Let's say I have I have a certain pressure here. I must maintain at the constant pressure. Yeah, constant pressure means must maintain at the same pressure. So let's say I start from here. Let's say I start from here. Okay, let's say I start from here. He say compress. He say compress. You see that? Compress, that means compress means what? Volume decrease, isn't it? Volume decrease. So for isobaric process, constant pressure, the graph can go, the graph can actually go to the right or go to the left. So go to the right or go to the left. But then he said compress at constant pressure. Isobaric constant pressure. So compress is a volume decrease. Look at the axis. Going to the right is volume increase, not volume decrease. Okay, going to the right is volume increase, going to the left is volume decrease. So the graph isobaric should go to the right or go to the left? Compress, so it's not going to the right. It's not going to the right. It's supposed to be go to the left. So this is the one. Okay, so should go to the left. Let me okay, so this is the correct one, go to the left. Okay, and then for the last one, isochoric process, constant volume. Constant volume, that means must maintain at, let's say okay, so constant volume, that means say same volume lah, same volume, isn't it? Same volume, same volume. Let's say I start from where? Let's say I start from here lah. Yeah, I start from here. Let's say I start from here. So so the graph should go up or go down? Should go up or go down? Which one? Go up or go down at constant volume? Here you say heating. You see that? Heating. Heating. So heating, that means the temperature increase. Heating, that means the temperature increase, isn't it? Becomes hotter and hotter. So the graph should go up or go down? If go down, it go from 400 Kelvin to 300 Kelvin, go to a low temperature. Okay, as I told you, when the graph going away and away from the both axes, pressure and volume axis, when the graph going away from the axis, when the graph going away from both axes, the temperature increase. So what I can say is, if I start from here, if I go up, means temperature increase. Temperature increase. If I go down, means temperature decrease. Temperature decrease. But this one is heating. Heating, that means temperature increase. Temperature increase. So the graph should go up, not go down. So this, the below one is wrong, so the top one is correct. Okay. So what I can say is, so I got 3 graphs already. You see that? I got 3 graphs already. So I can maybe I can combine. Yeah, combine roughly over here, below here. So start from, this is the first one. Look at this one. This is the first one. This is the first. This is the second. This is the third. Okay. So how going to draw it? So I start from the first one. Let's say I no need to draw the axis first. I just roughly sketch. You know, roughly sketch. Let's say I start from this point. Let's say I start from this point. So the first graph should go down like that, curve like that. And then what else? What else? He go and then go to the second graph. This just now is the first one, and then the second one is go to the left. Go to the left. Is it go back to the same volume? I'm not so sure. Maybe just sketch only. Okay, is it go back to the same volume? I'm not too sure. And then there's the second process, and then the third process is the graph go ups. You see, the graph go up. The graph go up. So the graph go up. I think go back to the original condition. Yeah, original pressure, original volume. So this is the third process. Go down, go to the left, and go up. Go down, go to the left, go up. I think the graph should be like this. Okay, now let's draw properly the graph. Okay, let's draw properly the graph. Okay, so this one just for reference. Drag it down already. So just now I want to draw the graph properly. I roughly sketch the idea over here. Now I draw properly with all the label, all the unit, all the values on the axis, and the graph properly. Yeah. So this is a pressure. Yeah. Look at the unit also. Be careful with the unit. Always be careful with the unit. You see liter. This is atmospheric pressure. You see that? So okay, my pressure is atmospheric pressure. Don't put Pascal. Must follow the question. Volume is liter. Okay, 0. And then Okay, so you know the graph should start from here. Follow this one, should start from here, then go down, go left, go up. So I should plot this 1 liter over maybe I should plot over here. Yeah, 1 liter is over here. Okay, how many say initial volume expand, then compress, expand. He didn't say what. Okay, never mind. This is a 1 liter over here. Start from here, isn't it? Start from here. So if your graph start from here, so your graph should be starting from here lah. Maybe I just plot first around here. Yeah. This is 1 liter and 3.5 atmospheric pressure. Okay. In 3.5 atmospheric pressure. Okay, start from there. Then I need the isothermal line also. I need to draw an isothermal line. Curve. I have a nice curve there. Yeah, I curve until here. Yeah, isothermal line. I don't know what temperature is it. Did he mention about the temperature? No. Never mind. Just put as T1. Okay, so expand until maybe until here. Should be acceptable. Okay, expand until become pressure 1 atmospheric pressure. So the graph should go down. Oops, sorry. Should go down. Wait, I need to use red color. Yeah. So yeah, this is the isothermal expansion. This is the the first one, isothermal expansion. Okay, so you need to label the value. You need to label. Did he say about this volume? No, he didn't say. So didn't say, just put as volume 2. And this one is volume 1. Yeah, volume 1 is volume 2. Didn't mention. So until 1 atmospheric pressure, you see, expand, become 1 atmospheric pressure. That means is over here. Yeah, this is 1 atmospheric pressure. Okay, 1 atmospheric pressure. Then compress at constant pressure back to the initial volume. So you go back to the initial volume, 1 liter. So compress. So graph go back to the initial volume. So the graph should go constant. You know, this isobaric constant pressure. Yeah, constant pressure. This is number 2, which is isobaric constant pressure back to initial volume. Okay, and then lastly constant just now constant pressure. Just now this one is constant pressure. Lastly is constant volume. Constant volume is isochoric. Constant volume, that means maintain at 1 liter. Okay, then go up. He go up to the, so you must highlight all this. This is initial volume, and this one go back to original pressure. You see that? Isobaric just now is go back to the initial volume. Yeah, go back to this point. So go back to 1 liter, but maintain constant pressure of 1 atmospheric pressure. Okay. Now the third one is constant volume. Constant volume, that means maintains 1 liter. But heating, go up to the original pressure. Original pressure is 3.5 atmospheric pressure. Go back up to the original pressure. So the graph should go up. So this is the third process. Which is isochoric. Okay, so I have all the values. I don't have this one yet, is it? Okay, so if I don't have, I need to, you cannot just leave it out. This is pressure 3.5, 1 atmospheric pressure. This is 1 liter. This what is this volume? So what I have to do is you need to find out what is this volume. So you use what? You use this is a isothermal process. Is actually what? It's actually this is actually Boyle's law, constant temperature. This one is a isothermal is constant temperature. Constant temperature. When temperature is constant, when isothermal process temperature is constant, that means only the pressure and volume changes, which is P1 V1 equal to P2 V2. So this one is P1 V1 P2 V2, which is, so the isothermal process is actually Boyle's law. Is actually Boyle's law. So you need to find the volume 2. We have already the we can put this as this one as pressure 1, this is pressure 2 lah. Okay, this is pressure 1, pressure 1, pressure 1, volume 1, pressure 2, volume 2. So we can find volume 2. Okay, so P1 V1 equal to P2 V2. Okay, we actually can maintain this unit. Yeah, you want to maintain this unit as this 2 unit you want to maintain as, because they have the same unit, isn't it? They have the same unit. Okay, what I want to tell you is this one you can maintain as atmospheric pressure. No need to change to Pascal. This volume you can put as liter. But the temperature, if you have a Charles law, like if you use another formula which is like V1 over T1 equal to V2 over T2, this actually we can say that this volume also you can put as liter, no need to SI unit, but this one must be Kelvin only. Kelvin only. Kelvin only. Yeah. Degree Celsius cannot. Okay. Degree Celsius cannot. Okay. This one you can put as atmospheric pressure when both side both side have same unit. Both side. This one both sides. So you can no need to change to Pascal, no need to change to meter cube for the volume. Yeah, because both sides have the same unit. But whenever you use the formula, you use back the formula of PV equal to nRT. Better you must change all this to SI unit. Change to this one, change to Pascal. This one change to meter cube. This one change to Kelvin. All must be SI unit. Only when you have left and right hand side have the same unit, atmospheric pressure, liter, they can cancel off the unit. You understand? They can cancel off the unit. So you don't need to bother about changing it to SI unit. But this one, better you change to SI unit only. But for this temperature, is special. Yeah, you cannot put degree Celsius. You must be in Kelvin. Why? Why is it so troublesome? Okay, why the volume can put as liter but can non-SI unit, but the temperature must be in SI unit? Because you see, 1 liter is 1 dm cube, isn't it? 1 dm cube, which is exponent negative 3 meter cube. You see that? It's multiply. It's multiply. You see that? I can say the important thing is the multiply. Multiply. But for the temperature, the temperature, let's say 100 degrees Celsius is actually 100 plus, it's not multiply, it's plus, plus 273 Kelvin. It's a plus. So like for temperature, you cannot cancel this one. You cannot left hand side and right hand side cannot cancel the plus 273. But the multiply, you can cancel both sides. You understand what I mean? I don't want to explain too lengthy about this, but I hope you get the sense. Because this temperature is a plus, you plus the value. But for this one, for volume, this one is about volume. This one is about temperature. For volume or the pressure also, pressure also is 1 atmospheric pressure is actually 1 multiply 1.013 exponent 5 Pascal. Also about multiply. You see that? Also about multiply. So things about multiply, you can cancel left and right. You can cancel left and right. Same as the volume, also you can cancel left and right. So no harm to the equations. But the temperature is a plus. It's plus 273. It's not multiply 273. This one, the things you plus one, you cannot cancel left and right. So this one for the temperature must be Kelvin only. Must only use Kelvin, cannot use degree Celsius. Okay. So to cut things short, and also back to these questions, this equation, when you use PV equal to RT, make sure you must change part pressure to Pascal, volume to meter cube. This one you must all in SI unit. Yeah, you cannot atmospheric pressure and liter. Yeah, this one can, because this one left and right hand side you can cancel the unit. But this one you cannot cancel the unit. You cannot cancel the unit because the R here, the Rydberg constant, this R value is in SI unit. How should I write? This R is in SI unit. So all the other must be in SI unit. Okay? Only this one you can maintain as atmospheric pressure and liter. Okay? So that's all for remember, this one you must change all to SI unit. This one you can no need to change it to SI unit to make things easier. But for temperature, you cannot say cancel both sides. Yeah, because if you use Kelvin, the value different already. You use degree Celsius, the value different already, because it's plus sign. It's not multiply sign. So this one must be in Kelvin. Temperature must, no matter how, must be in Kelvin. Must be in Kelvin, cannot degree Celsius. But for the volume here, you can maintain as liter because you can cancel both sides. The multiply exponent -3. Okay. Okay, go back to using this one to find the V2. Okay, we can maintain as atmospheric pressure and liter. Okay, so let's do it. Yeah, pressure 1, volume 1, pressure 2, volume 2. Let's do it. So my pressure 1 is 3.5. Yeah, look at my one. Pressure 1 is 3.5 atmospheric pressure and 1 liter. 3.5 atmospheric pressure and 1 liter. Okay, and then this one is pressure 2. Pressure 2 is 1 atmospheric pressure. 1 atmospheric pressure, and this one is volume 2. Let's find out the volume 2. Yeah. Let's find the volume. Hey, I think this one is easy because 1. So this one should be what? His volume 2 should be 3.5 liter, isn't it? Should be 3.5 liter. 3.5 multiply 1 is 1 multiply 3.5. Okay. So it's easy. So this one is, I can put this one as 3.5 liter. This is volume 2. So I got all the, no need to find the temperature lah. Yeah, no need to find temperature unless it's required. So this is the graph. 3.5 atmospheric pressure, 1 atmospheric pressure, 1 liter, 3.5 liter. Okay, so that's all for these questions. Hope you understand what I'm talking about. Okay, so you can separate it to 3 different processes. You draw individually first, predict, and then combine all them to one, and then from there you draw your proper graph. Okay, so that's all for this question. Thank you and bye.